Hello everyone, it's a pleasure to have Francesc Perera from UVA in Barcelona. So Francesc is going to talk about traces on ultrafilters of sister algebra. Francesc, please.
Okay, thank you very much. It's ultrapowers, but anyway, yeah.
Oh, okay.
Yeah. I will use ultrafilters though. Okay, so, well, first of all, thanks for having me here and inviting me to give a talk. And I will report on this joint work with Ramon Antoine, also in Barcelona, Leonard Robert, and Hannes Thiel. So all along the talk, A will be a unital sister algebra, and U will be a free ultrafilter on the natural numbers. Okay. So given this, we can form the ultrapower rather, of A. And this can be taken as the product over the natural numbers, quotient, the set of sequences here, such that they go to 0 along the ultrafilter. Okay. So that's a unital sister algebra as well. And well, why do we care about this? Well, it's a nice object and it appears in various places. So I will just mention some of them. So some uses of ultrapowers for places where it appears more or less naturally. So first of it, it's used a lot in logic and model theory. So they use ultrapowers a lot there. And well, I won't say much about this because I might say something wrong, so I don't. So then it also appears in when one studies the central sequence algebra, and that's also an important object. So this is, you take the ultrapower and then you take the copy of A inside here as constant sequences, right? And you look at the elements that commute with A. And well, for example, this is important in the sense that, for example, to detect if a sister algebra is Z stable, that's the same as saying that Z embeds unitally inside the sector sequence algebra of A. And it's also important in other instances. Another example where this happens is in Kirchberg's O infinity absorption theorem. Of 1993, where, I mean, well, I mean, he proves that if A is severable, simple, and nuclear, and purely infinite, then A absorbs O infinity. And an ingredient of the proof, I mean, the proof is deep, but an ingredient of the proof uses that the central sequence algebra or an ultrafilter of such an algebra is also what admits an embedding of O infinity. Okay, so it's used there. And well, another use of the second of ultrapowers also appears in other instances, and one of them I will spend some time with this because I will use it later, is in nuclear dimension. So one can write nuclear dimension in a way, so the use of ultrapowers admits to like pack certain definitions and not to have them like depending on various epsilons and deltas. So it makes you things that if you had to unpack them, then it's more complicated to write proofs and things like that. So, for example, there's this result by Robert in 2011 that says that so the nuclear dimension of sister algebra is less than or equal to n, if and only if so there exist finite dimensional algebras and k, where j goes from 0 to n and k is in n, and also CPC or the zero maps call them psi j and phi j, such that when you write this diagram, so you consider A included in the ultra power, and then you go down by psi j into now the ultra product of this fj case. So k runs in the ultra filter here, and then go up. We don't quite have that this commutes, but we have that iota, sorry, is the sum exactly of doing phi j, psi j, followed by phi j. Okay, so that's something that is an equality on the nose, and one doesn't have to be approximated things. Right? So that's one of the useful facts that one can use, right? I mean, okay, so ultra powers are interesting objects, and since we sort of care about them, want to know things related to this, and so the following is the problem that we consider in this work is the following. The problem is to compute the tracer state of the ultra power of a sister algebra. So the tracer state. And well, this can be divided in like two sub-problems, or maybe one sub-problem. So more specifically, what one would say is that can we determine this ultra power in this tracer state space, tracer state space, I should have said. So can we determine this in terms of the tracer state space of A and the ultra filter? Right. So that's the question we want to address. Okay. And to do so, I mean, we find a natural map from an object that depends only from the tracer state space and the ultra filter to the tracer state space of the ultra power. And then we see when this is, this natural map is actually an isomorphism. So it's k that runs through you. Yeah, j runs from 0 to n. Yeah, so at each stage you have f0k direct sum f n k. This is what this means.
I was confused about that.
Yeah. It's not. Yeah, but this is what it means. So there's a natural map from well, the ultra coproduct of the trace space of A. I will explain what that is, to the tracer state space of the ultra power. So that's the ultra coproduct. So how is this map defined? So I will spend some time with this. So the first thing is to write the actually the ultra power in some sort of categorical way. So ultra product from the categorical perspective. And well, the first thing is that we have so since U is an ultrafilter, in particular, it's closed under sections, its members. So if E1, E2 are elements in U, then the intersection is in U, and also if E1, E2, and E1 belongs to U, then E2 also belongs to U. Okay, so if we have now E included in F, say in the ultrafilter, then we get a map from the product of A in F to the product of A indexed only by E, right? So then we get this. And we simply forget, so forget the elements in F, no, right? And this, one can then take the elements in U and have a net, and we get a net by saying E is, well, maybe I should write it like this, by ordering like this, even only if E is included in F. And with this, we get an inductive limit. So we can get an inductive limit now of these products of sister algebras, right? So this is now a net with disorder, and we have these connecting maps here. And one can prove that this is the same as the ultra power of A. So the definition that I gave you first here, which is more like a hands-on definition, is the same as this more abstract thing. So as a categorical perspective of the product. Now, if we have this, we can so we have this thing. Let me write it like this. F, A. This goes to the ultra power, and then we can turn this around by taking traces. So now we have traces here, and of course this is contravariant, so we get traces here, and we get an inverse limit like that. And now, of course, now in order to understand this, we want to understand each one of the blocks, right? So now we have now the trace of A, the tracial state space of A. We can take the coproduct of this over F. And this is like, this exists in compact convex sets. So this is the coproduct of compact convex sets, which is basically saying that every element here is like the closed convex hull, or the direct convex sum of the elements in here, in a kind of a unique way. One can describe this. And then by the universal property of coproduct, we have a map from here, from this coproduct to this tracial state space. And then, of course, by the same argument as before, we get also a map this way, so these maps exist. And then we can take the inverse limit. And this is by definition the ultra coproduct of these coproducts of spaces. And then by properties of inverse limits, we get a map. So this is the map phi I was referring to before. Right? So this map exists by some universal property of inverse limits. Right? So that's one way to describe this. And then what do we have? So we have that, well, is this proposition that this map phi, so this map is always injective. So one can prove this. And then, of course, the question becomes, so the problem I was referring to right there is now, when is this surjective? Because this gadget here is determined by the traces of A and the ultrafilter, right? So one wants to ask when is phi surjective? Or also, if it's not surjective, I mean, we can say at least, well, it's implicit in kind of the question, what is the image? Fine. Okay. Okay, and for this, well, there's a definition that comes in handy. So suppose that we have, so this is the way of actually a naive way of producing traces in the alpha power. So one has traces in A. So if you have a sequence, sorry? Is the image of phase?
Yeah.
Oh, the image of phi. In general, yeah. Well, we can characterize when it is surjective, but whether the image is always a phase or not, I'm not sure. Maybe. Yeah, that's a good point, I think. Yeah. So if we suppose that tau n is a sequence of traces, on A, and if we take now pi n, the projection from the product of A to A, the product of A's to A, so that's a projection onto the nth coordinate. Then, of course, we take by n followed by tau n. So this gives, or is a trace actually, which n, right? Is a trace, we call this maybe tau n bar. So it's a trace on here. And we get in this way a sequence of traces on the product. And now one can verify, so using that this thing is a compact space, so we get a limit, right? So the limit of tau and bar exists, right? Because it's a limit along the ultrafilter. And one can also verify that this vanishes. Tau bar. I mean, I should call it. Yeah, we'll just call it limit. This thing also vanishes on this ideal C sub u that I was referring to in the beginning. So this vanishes on this CU. So this was this sequences as at the limit. They go to norm, they go in norm to zero along the ultrafilter. So it induces, so we get then a trace on the outer power. So for each sequence of traces, one gets a trace in the outer power constructed in this way, right? So we denote by the limit traces. So this is a set of traces constructed as above. Okay, so that's a subset of the set of traces on the outer power, right? And this can be actually quite big, as I will mention now. So in particular, the proof that the following proposition is that the image of the map is precisely the closure of this set in the Weak-Star topology. Right, so that's on what gets in general. So now the question of when this is surjective becomes to know whether this thing is dense, right? So the question is now, when is the set of limit traces dense in the set of traces of the algebra? That would be the thing. And this has been considered before and has been studied. And there are some partial answers. So the first results. First one, and the sister for sister algebras would be due to Ozawa in 2013. And he proved that, there's density. So in the case, if A is exact and Z stable, then this happens. So the map is surjective. A second result is due to Ping Wang-Ying and Leonel. I think this is in 2016. where they proved the same if A has a strict comparison by traces. And finally, Archibald, Robert, and Quizzes in 2017. Yeah. Also in the case, if A has finite radius of comparison. So in all these situations, one has that this subset is dense. And just to illustrate what this can give, for example, if one had a monotracial algebra, like a remark, so if we know that we have a monotracial algebra and say, for example, A is exact, it's stable, just to be in one of these settings, then what is this? Well, this is the closure of this thing, but this thing can only have one trace because there's only one trace here. So that's only precisely this tau u, which is constructed out of this tau here. So we only have also one trace here in this ultrapower, in this case. Okay, so what is the result we prove? Well, we prove that one can characterize precisely when phi is an isomorphism, but also in terms of other aspects. One of them is using some relations in the Kuhn semigroup of T algebra. I will mention. This. So this is the theorem. So the following equivalent. So the first condition is that, well, I will just repeat this from the ultra coproduct of the trace space to the trace space of the ultra power. This is an isomorphism. It's the same as saying that the limit traces is dense. It's just summarizing what I was saying before. And the third condition is that one can find a number such that for every n, so this is a natural number, so that for every element in the closed linear span of the commutators, we have that one can approximate this A by the sum of some commutators by less than or equal to half the norm of A. And this is for some, of course, Bj, Cj in A. And the norm of Bj, the norm of Cj is also less than or equal to norm of A. So the thing here is that we have this quantifiers switch around. So if for every element like this, of course, one can choose finally many commutators that this approximates by definition, right? So the thing here is that one can fix a uniform n that will work for every A. And that's the point of the result. And this comes after having this density. So, of course, I mean, also writing things exactly as sums of commutators, this has been done, studied by people in set stable sister algebra. I think it's Ping and Leonel also studied this, and they proved that every element can be written as a sum of 7 commutators, something like that. So, and so furthermore, so if now one assumes that all quasi-traces are traces, so this is implied by, as we know, but just mentioned, so if A is nuclear or exact, we want to assume this. So assuming this, then we have all quasi-traces are traces, and then these 3 equivalents, these 3 conditions, sorry, are also equivalent to 2 more conditions, and these have to do with the Kuhn semigroup. So with 2 comparability questions, 2 comparability conditions, sorry. That's first one, is that if you take any epsilon and any d in the order of numbers, then there must exist an n such that whenever you have, well, I will explain this notation now. So then, so where does this happen? So this happens x, y in the Kuhn semigroup of A. So this is constructed similarly as the Moray von Neumann semigroup by using positive element instead of projections and a natural equivalence relation. And one wants also that x is less than d times the unit. So that's this d is, one can think of, okay, this x is like a positive element coming from d by d matrices, and also 1 is less than or equal to d times y. So this is to be interpreted as y is not too small. So what is this saying? Well, that x and y compare not on the nose in the semigroup, this has an order, but compare trivially. So meaning that if x sits trivially below or almost below y, then one can compare actually x and y maybe after amplifying by some number. And that's what this is saying. X hat is the tracial representation of x, kind of. So x hat would go from the functionals, yeah, from the functionals of C of A. So every functional you evaluate. There's a tracial version of x. And this is like, well, the d taus corresponding to traces. Satisfying this, yeah. Going from, no, for this x's, if this happens, then this happens. Yeah, right. I guess so, yeah. 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 So it means that typically you want to know if some things compare trivially, you want to know what happens with the order. That's a very usual question. And in this case, you say, okay, if x so these are functions, and of course you can multiply by some number. So if this function compare, but this is below, but slightly below, then you can actually compare them. But this holds for the x's and y's, so that x is like in d by d matrices and y is full, kind of. So it's not too small element. And the other condition, which is formally stronger, is actually you can find an element, a natural number, which works universally, such that for every d, again, to be interpreted as d by d matrices, there exists an n for which now I only want x to compare trivially with y, and this implies that x is nx. Now I want to compare this with ny, and I can do this, but after amplifying and multiplying the amplification by n. And again, this is for the same thing. Right. And well, I said it, but just in case. So this is a constant group. Right. And okay, in the last part, I want to see some applications of this. Well, one of them is more clear. The other is kind of hidden in the sense that I cannot show what it, well, I mean, it would take a while to show where this appears. So this has to do with the notion of pure system algebras. Okay. So
number 4, I think, I guess that's obviously implied by finite real comparison.
Yeah, you get finite result.
Finite real implied 4.
Yeah, the other one, no, it's not clear.
Kind of a weak version of finite real comparison.
Oh yeah, that one could actually analyze, I mean.
But
that one could actually analyze, or?
No, I mean, I'm saying it's kind of a weak version of finite real comparison.
Yeah, you get that, but it's not equivalent to that. Yeah. Sorry.
There's a notion of n comparison. I hear you somehow saying that if you have something, you can find n n comparison.
Yeah, well, I mean, kind of, but you have to amplify. So.
Oh, I'm sorry. I said that was number 4.
Also here, you have to amplify, no? I mean, n comparison would appear on this side, I think only. Right? Well, I will get into this now. So I was going to define. So this goes back to Wilhelm Winter, I believe. So we say that A has M comparison if whenever you have an element X and M plus 1 elements in the cool semigroup, the condition that X hat is less than or equal to, and for every epsilon, I should say, the condition that X compares trivially with Yj, with all the Yj's in this way, so it's almost below for all J, then this implies that X is less than or equal to the sum of the Yj's. So a corollary to this result is that if the finite A has finite nuclear dimension, and this is less than or equal to M, then the trace space of the ultrapower is the same as the ultracoproduct of the traces. So in other words, phi is ISO, right? So how does one show this? So that's at least something one can write. So to see this, so we can, well, I mean, we know there's a theorem by Leonard Robert, also in 2011, that if you have finite nuclear dimension less than or equal to M, then A has M comparison. Okay, so that's known, and now let's verify this condition here. So in order to see that we have something like so the isomorphism, we need to see one of the conditions. So we need to fix this M, and now we just let M to be 2 times M plus 1, which is this number, so this is something fixed, and we let N equal to 1. Now, if X hat is less than or equal to Y hat, so take these elements here, but that's not so relevant here for this argument. So if this happens, then we can write this as 1 minus a half times 2, which is 1 minus a half times this. So X hat is less than or equal to 1 minus epsilon times something hat, right? And now we can apply the M comparison result. So we can take Y to be constant all the way. So this implies that X is less than or equal to 2Y. So it's 2Y multiplied by the number of copies we have, which is M plus 1, right? So this is 2 M plus 1 Y. So that would show that if one has this, then we have isomorphism here. Okay. All right. So, and the other notion to define pureness, which we haven't defined yet, is that of divisibility. So this one also due to Wilhelm Winter. So one says that A is indivisible if for every X in the Kuhn group of A, and for every what is called cut down, so something which is compactly contained. So the example here is if you think that X is the class of positive element, a typical cut down as by taking, A shifted to the right by some epsilon. So whenever we have this, and whenever we have this, and for every, so given K in N, so then one can find a Y also in the Kuhn group, such that AY is less than or equal to X, and X prime is less than or equal to k plus 1 y. Oh, sorry, I have to amplify this by n plus 1. So this is the so n divisible means that you have to amplify y. So the best form of divisibility is when you have 0 divisible. So 0 divisible means that actually we have ky less than x, and x prime is less than or equal to k plus 1 y. So it's kind of, we can almost divide x by k, right? So we can find this element which approximates, k times this element approximates x, and this other element which is very close to x is also approximated by k plus 1 y. That's the rough idea of this. And zero comparison is also I should have said that before, is also the best possible comparison, which means really that if x and y compare, then in this fashion, then actually x is less than or equal to y. It's the possible best comparison, also called almost unperforated. So this property is also called, known under this name. So it's perhaps worth noticing that if you have an almost unperforated full semigroup of a sister algebra, so it's just a remark here. So if C of A has zero comparison, then zero divisibility. So being able to divide like this is equivalent to a slightly better form. It's the same as saying that for every k, you can find a y, such that k times y is not equal to x, is not equal to k plus 1 y. Right? So one can avoid the use of these kind of obnoxious cut downs. So x is more or less divided by k. That's the idea of this property. Okay, so we need to define the notion of pureness. So a sister algebra is Mn pure by definition if it has M comparison and N divisibility. Right? So you can compare up to this M amplification, and you can divide up to this N amplification. And A is pure, or sometimes also called 0, 0 pure. Well, said pure if it's 0, 0 pure. So one has the best comparison and the best divisibility. Okay. Right. And oh. Okay. So what it was the result? So a couple of theorems, and then this was proved by Winter in 2012. So in the case you have simple separable and so simple separable sister algebra A with a locally finite nuclear dimension and Mn pure, right? Then A is Z stable. And in fact, a much earlier result due to Michael Rodan, 2004, is that if A is Z stable, then A is pure. So you have almost non-proliferation and almost divisible Kuhn seminar. So put this together, so a simple separable locally finite nuclear dimension, right? So Mn pure implies pure. Okay. So, and using our methods and the ultrapower techniques in particular, one is able to remove this part. So that's, we prove. Yeah, unit all the way, yeah. So if A is simple and unital, yeah. So then Mn pure implies pure. And that's kind of a statement that doesn't involve ultrapowers at all, but they appear in the arguments. And yeah, I mean, that should be it. Thank you.